You've seen them before? Those massive ships sitting just offshore, not docked, not moving, just sitting there. And if you've ever looked closely at the front of one, you might have noticed a huge chain disappearing down into the water. That chain is attached to something sitting on the bottom of the ocean that weighs more than a fully loaded semi-truck, sometimes a lot more. This is one of those things hiding in plain sight on every coastline in the world. And the engineering behind it is far more interesting than most people ever stop to wonder about. Today we're talking about ship anchors, how they actually work, why ships anchor where they do and not just anywhere, and why dropping 30 tons of iron to the seafloor is only part of the story. Let's start with the most important thing most people get completely wrong about anchors. An anchor does not hold a ship in place by being heavy. That sounds backwards, so let's slow down on it. When you picture an anchor in your head, you probably imagine this enormous metal weight sitting on the seafloor, and the ship being held still because that weight is so massive, it simply can't move. That's not how it works. Not even close. Modern ship anchors hold vessels in place almost entirely through grip and geometry. The anchor buries itself into the seafloor, into the sediment, the mud, the sand. And it's the resistance of that seafloor material against the buried anchor that provides holding power. The weight of the anchor is almost secondary. What matters is how deep it buries, how wide it spreads, and how effectively the seafloor material locks around it. Think of it like trying to pull a shovel out of wet sand. If you pull straight up, it comes out relatively easily. But if the handle is angled away from you and you pull along the angle, the resistance is completely different. The geometry changes what you're fighting against. That's exactly the principle behind anchor design. The most common type on large commercial ships is called a stockless anchor. The classic shape with two broad flukes angled out from the shank. When it hits the seafloor and the ship begins to pull on the chain, those flukes dig into the sediment and rotate downward. The deeper they go, the more sediment they fight through. An anchor buried 18 inches into soft seafloor clay is holding with forces that its own weight could never achieve. Some modern, high-holding power designs can generate holding forces 15 to 20 times their own weight, meaning a properly buried anchor is fighting the seafloor itself, not relying on gravity. Now here's where it gets even more interesting, and where the chain comes in. The enormous chain connecting the anchor to the ship isn't just a connector. It's doing critical mechanical work. A large ship might deploy 300 to 400 feet of chain when anchoring. The weight of that chain lying on the seafloor ensures the pull on the anchor stays horizontal rather than vertical. If the chain pulled upward at an angle, it would lift the flukes right out of the sediment. By lying flat along the bottom, the force on the anchor always comes from a horizontal direction. The flukes stay buried. The anchor stays put. Then the chain is what makes the whole system work at scale. And here at Plainly Put, this is exactly the kind of engineering hiding in everyday things that we love to dig into. If you want more of this every week, subscribe. We're here every Tuesday and Friday. Now the anchor itself, because 30 tons is worth a moment. The anchor on a large container ship or oil tanker can weigh 20,000 kilograms, over 45,000 pounds. Most large ships carry two of them, one on each side of the bow. The chain is proportional. Each individual link can weigh 400 to 600 pounds. A full deployed length of chain might weigh 100 tons on its own. When a ship drops anchor, it's not just sending the anchor to the seafloor. It's sending 150 tons of iron down with it. The chain is stored in a compartment called the chain locker deep in the bow, deployed through a reinforced steel tube called the hawse pipe and controlled by a massive hydraulic winch called a windlass. Hauling everything back up generates hundreds of tons of pulling force and can take 20 to 30 minutes of continuous operation just for a routine anchorage. So why does any of this matter? Why not just dock somewhere? This is where the story connects to the global supply chain that moves almost everything you own. At any given moment, thousands of ships are waiting at anchor in approaches to major ports worldwide. They're not broken down, they're not lost, they're in a queue. Port terminals have limited berths. Ships arrive on schedules that don't align perfectly with available dock space. Customs processing, cargo documentation, berth assignments, tidal windows for deep draft vessels. All of these create waiting times. Anchoring in a designated roadstead near a port is far cheaper than burning fuel steaming in circles. Those anchorage areas aren't chosen randomly. Captains and harbor pilots select them based on 4 specific factors. Depth. You need enough water under the keel without so much depth that the chain can't work effectively. The rule of thumb is 5 to 7 times the water depth in chain length on the seafloor. In 30 meters of water, that means 150 to 200 meters of chain deployed. At extreme depths beyond 80 or 90 meters, conventional anchoring breaks down entirely, which is why offshore oil platforms use completely different mooring systems, involving torpedo anchors and suction caissons engineered specifically for deep water sediments. Bottom composition. Sand and mud hold well. Rock holds poorly. Certain seabed conditions can foul an anchor, catch it under a ledge, or tangle it in old chains from previous vessels. Nautical charts mark bottom composition with specific symbols, and a good anchorage has a soft, uniform seabed, protection from weather and current. An exposed anchorage in open water with strong tidal currents constantly shifts forces on the anchor, increasing drag risk. A protected bay with stable currents lets the system settle without stress cycling. Swinging room. A ship at anchor doesn't sit still. It swings around the anchor point as wind and current shift. A fully loaded supertanker might need a swinging circle of 500 meters or more. Captains have to calculate that radius and ensure no other vessel is anchored within it. One anchor dragging, when the anchor loses grip and begins sliding, is one of the most dangerous situations a ship can face. It typically happens when unexpected weather hits faster than the crew can respond. Modern ships carry anchor watch alarms that alert the crew if the vessel drifts beyond a set radius. But dragging can happen fast. In a crowded anchorage, a dragging ship is a hazard to everything around it, and harbor pilots monitor anchorages closely in storm conditions. For exactly this reason, there's a dimension most people never consider: the environmental impact. In areas with coral reefs or seagrass beds, a dragging anchor can destroy in minutes what took decades to grow. Many marine protected areas now require large vessels to use mooring buoys connected to permanent seafloor moorings rather than free anchoring. In places like the Florida Keys and the Great Barrier Reef, the damage from decades of unregulated anchoring has required expensive restoration. The newest ships use dynamic positioning, GPS, and computer-controlled thrusters that hold a vessel in place without any anchor contact with the seafloor at all. And anchors get lost more often than most people realize. In rocky bottoms or strong currents, an anchor can become irretrievably fouled. The ship slips the chain and moves on. In heavily trafficked anchorages, the seafloor can be covered in lost chains and old gear from previous vessels going back decades. Or in historic anchorages like the Downs off southeast England, going back centuries. Roman anchors have been found in Mediterranean sediments, still roughly anchor-shaped after 2,000 years. New anchors dropping into old debris fields can foul immediately, which is one reason choosing a good anchorage is as much art as science. Step back and look at the scale of what's happening right now. Thousands of ships worldwide connected to the seafloor through 150 tons of iron chain each. Every anchor designed with precision geometry to bury itself at exactly the right angle. Every placement chosen using charts that encode centuries of accumulated knowledge about seafloor conditions and tidal patterns. All of that invisible engineering, sitting silently below the waterline, is what keeps the global supply chain moving. The ships waiting offshore aren't idle. They're holding position in the queue that delivers the clothes in your closet, the food in your kitchen, and the electronics on your desk. And the only thing keeping them from drifting is a buried piece of steel and a chain lying flat on the seafloor. Not a weight, a buried lever. One of the most quietly essential pieces of engineering in the modern world. And that, plainly put, is why ships anchor where they do, and how a 30-ton anchor actually works. If that changed how you think about what you see out on the water, share it with someone who's ever watched a ship sit offshore and wondered why it doesn't just pull into port. And if you want more of the real science behind how everyday things actually work, Plainly Put is here every Tuesday and Friday. Subscribe, and we'll see you next week.